All right, so get ready. We're diving deep into the life of Richard Feynman. You've sent over some excerpts from a biography of him, and wow, this guy, I mean, he was more than just a brilliant physicist, right? Like, he was a total enigma.
Yeah, you know what's so captivating about Feynman is that he was a genius, but he was also really playful.
Yeah,
He never lost that childlike curiosity, and it really fueled his groundbreaking work in quantum physics.
for sure, for
Yeah.
sure. And the excerpts that you sent over, they really show that, you
Yeah.
know? And in this deep dive, we're going to explore how Feynman helped us understand the bizarre quantum world.
Yeah?
His work on the theory of light and matter,
Okay.
which is quantum electrodynamics, QED,
Right.
his work on superfluidity,
Wow.
and even his early visions of nanotechnology.
It's truly remarkable how much ground this guy covered. I mean,
Right.
each of those areas, that would be a career for most physicists.
Yeah.
But Feynman tackled them all with incredible insight.
Yeah, totally. So let's start at the beginning. Feynman was born in Far Rockaway, New York, back in 1918.
Okay.
And the biography talks about how his father, instilled in him this deep curiosity
Yeah.
and encouraged him to question everything.
That's crucial to understanding Feynman.
Hmm.
It wasn't just about accepting what he was taught, but about constantly probing,
Yeah,
looking for those deeper explanations.
for sure.
Yeah.
And it's clear he showed a real knack for math and science early on.
Oh,
Like
yeah.
when he was at MIT, he stumbled upon this thing called the principle of least action,
Yeah, the principle of least action. That's a good one.
which honestly, it sounds pretty complicated.
It is. It is.
Yeah.
But think of it like this, okay? Imagine you're throwing a ball.
Okay.
That ball could take an infinite number of paths to get to its destination.
Yeah, yes, so.
But in reality, it takes the most efficient path,
Oh.
the one that uses the least energy.
Right.
And that's basically the principle of least action, And that ended up being like a cornerstone of Feynman's work.
So even in simple things like throwing a ball, there's this deeper principle at work.
Exactly. Yeah.
Wow, okay. So after MIT, Feynman went to Princeton for his PhD,
Right.
and that's where he met John Wheeler,
Oh, ew.
another incredible physicist.
Yeah.
But even Feynman hit a wall when it came to understanding quantum mechanics, which at the time, was turning the world of physics upside down.
Yeah, it was a massive shift. Classical physics,
Yeah.
but the physics of everyday life.
Right.
It just couldn't explain what was happening at the subatomic level.
Yeah.
Like take the double slit experiment, for example.
Okay.
Imagine you shine a light through two tiny slits.
Yeah.
You'd expect what? Two bright spots on the wall behind it, right?
Yeah, that makes sense.
But that's not what happens with electrons.
Wait, what does happen?
Instead of two distinct spots, you get an interference pattern.
Oh.
It's like waves overlapping. It's as though each electron goes through both slits simultaneously. Yeah, it was mind-boggling, And even Feynman initially struggled to wrap his head around it.
So electrons act like waves and d particles.
Exactly.
That's just weird.
It is. It is. It's called wave-particle duality. And it's one of the central mysteries of quantum mechanics.
Wow.
And physicists were grappling with, how to describe this mathematically.
Yeah, right.
Dirac's equation, which is this complex mathematical formula, was a step in the right direction, but it wasn't the whole picture.
I remember reading about these things called virtual particles. What are those exactly?
Virtual particles.
Yeah.
They're like tiny ephemeral particles constantly popping in and out of existence, almost like a quantum foam
Okay.
underlying reality.
Right.
And they're not directly observable,
Okay.
but they have a real impact on how particles interact.
Oh, I see. Okay, so I'm starting to see why even someone like Feynman found this stuff challenging.
Right.
And from what I've read, those virtual particles caused major headaches when it came to calculations in QED, right?
Yeah, you're right. They were leading to these nonsensical infinities,
Yeah.
making it impossible to get, meaningful results.
Right.
And that's where Feynman's boldness comes in,
Okay.
He started wondering if the electromagnetic field itself, the very foundation of how we understand light and magnetism,
Right.
what if it was actually just a convenient fiction?
Oh, okay.
What if, instead of being this fundamental entity, it emerged from the direct interactions of charged particles,
Okay.
like those virtual particles we were just talking about?
So it's like saying the stage isn't real, only the actor.
Exactly.
Wow, that's a pretty radical idea.
Yeah, it was a radical idea.
Yeah.
But, Feynman was never afraid to challenge the status quo.
Yeah, that's for sure. Now, while all of this mind-bending physics was happening,
Yeah.
Feynman's personal life took a dramatic turn when he fell deeply in love with Arlene Greenbaum.
Ah, yes, our lie.
Yeah, their love story is both heartwarming and heartbreaking, especially in the face of Arlene's tuberculosis diagnosis.
It is. It is a tragic love story.
Yeah, and those letters in the biography that really painted a picture of their relationship.
Oh, yeah, yeah.
You know, knowing her illness was serious, they still decided to get married.
Right.
Can you imagine the mix of emotions on their wedding day?
It must have been incredibly bittersweet. Really tough.
Yeah, and then right as Feynman's career was taking off, World War II breaks out.
Right.
And he gets recruited to work on the Manhattan Project at Los Alamos.
Yeah, the Manhattan Project.
The top secret mission to build the atomic bomb.
It's hard to even fathom that, you know?
Yeah.
Like he's working on this incredibly impactful scientific development
Right.
while also dealing with Arline's declining health.
It really highlights the human side of Feynman, you know?
Oh, absolutely.
He wasn't just this abstract genius.
No.
He was dealing with real-life complexities.
Real-life stuff.
And emotional turmoil.
For sure, for sure.
And at Los Alamos, he met Hans Bethe, another brilliant physicist.
Oh, yeah, Hans, but...
Yeah. Bethe was known as the battleship for his very methodical approach.
Right, very methodical.
While Feynman was more like a mosquito boat, you know?
Yeah, darting around with his insights.
Darting around, exactly. You can almost see their contrasting personalities clashing and collaborating.
You know, their dynamic, it speaks to the different approaches within science, right? You need both the meticulous, step-by-step thinkers and those who can just, like, leap ahead with these intuitive ideas.
Totally, totally. But tragically, Arlene passed away while Feynman was at Los Alamos.
Oh, yeah.
And the letter he wrote to her after her death, it's just gut-wrenching.
It is. It is.
It's a stark reminder that even the greatest minds are still human.
Right.
Still vulnerable to life's joys and sorrows.
Absolutely. It's a side of Feynman we often forget.
Yeah, and it's important to remember.
Yeah.
Because it shaped who he was, how he approached his work, and how he saw the world.
It really did, yeah.
Absolutely. After Arlene's death, Feynman went through a period of deep depression.
Yeah, understandably.
He eventually found his way back to physics, moved to Cornell University,
Okay.
but he still faced the challenge of putting his groundbreaking ideas into publishable papers.
Right, right. You know, his thinking was so unique and intuitive.
Yeah.
Translating it into the formal language of those scientific papers.
Right.
It was a hurdle in itself.
Yeah, totally.
So that's where the 1947 Shelter Island Conference comes in.
And this was a major turning point for QED, right?
It was. It brought together all these leading physicists, and it was there that the idea of renormalization emerged
Okay.
as a way to deal with those pesky infinities that were plaguing the calculations.
Right.
The complex concept.
Yeah.
But imagine trying to measure something infinitely large.
Okay.
You need a way to, like, tame that infinity, you know,
Right.
to get a meaningful measurement.
So renormalization is like creating a ruler for infinity.
That's a good way to think about it, yeah. It involved subtracting infinities
Okay.
in a very specific way.
Right.
It was controversial at first,
I bet.
but it worked. It allowed physicists to finally make accurate predictions
Wow.
that actually matched experimental results.
This sounds like a mathematical high-wire act.
It was a major breakthrough.
Yeah.
And Feynman, along with Julian Schwinger and Shinichiro Tominaga,
Okay.
they all played crucial roles in developing different approaches to renormalization.
Wow.
And then a young physicist named Freeman Dyson,
Okay.
he came along and showed that all these approaches were actually equivalent.
Wow.
He was like a translator, connecting the dots between these seemingly different methods.
So they were all speaking the same language, just with different accents.
Exactly, yeah.
Wow. Okay. And on top of all the complex math, Feynman also introduced these things called Feynman diagrams. I remember seeing them in the biography. They look like little stick figures having a party.
Yeah, they might look simple,
Yeah.
but Feynman diagrams were revolutionary.
Okay.
They were a way to visualize subatomic interactions. You know, they're more than just pretty pictures, though. They provide a shorthand for the complex mathematics underlying QED,
Oh, okay.
making it easier to understand and work with.
So it's like he found a way to make the invisible world of quantum mechanics visible.
Yeah, exactly.
Okay, so we've got Feynman cracking the code of the quantum world,
Right.
taming infinities,
Yeah.
visualizing the invisible. But Feynman wasn't one to rest on his laurels, right?
No, not at all.
So his curiosity pushed him to explore other areas of physics, including the strange and fascinating world of superfluid helium.
Yeah, superfluid helium. That's one of those things that just makes you question reality.
What do you mean?
Well, it can flow without any resistance.
Huh.
It can climb up the walls of a container.
Really?
Yeah, it seemingly defies gravity. It's like a liquid ghost.
That sounds crazy. How did Feynman even begin to explain something like that?
Well, he brought his unique perspective and his path integral formulation of quantum mechanics to the problem. And instead of focusing on individual particles, he thought about all the possible paths they could take.
Right.
It's like imagining every single route a drop of water could take down a mountain.
Okay.
And
Yeah.
then finding the most probable path.
Right.
This led him to the concept of quasi-particles,
Okay.
which are kind of like collective motions in matter
Right.
that behave like individual particles.
Okay. So instead of individual dancers, it's like the whole dance floor moving as one.
You got it. And using this approach, Feynman was able to explain superfluidity in a way that made sense, even predicting the existence of rotons.
What are those?
They are these tiny whirlpools of energy within the superfluid.
Okay.
And later, experiments actually confirmed their existence.
Wow. Okay, so we've got Feynman cracking the code of the quantum world, taming infinities, visualizing the invisible, and then explaining this bizarre liquid that seems to break the rules of physics.
Yeah, it's pretty amazing.
But the world of particle physics was about to get even weirder with the discovery of strange particles.
Oh yeah, these new particles, they were throwing a wrench into all the neat categories that physicists had created.
Really?
Yeah, they were behaving in ways that no one could explain, forcing everyone to rethink their models.
So how did they even begin to approach that?
Well, that's where Feynman's intuition and Murray Gell-Mann's theoretical brilliance would clash and eventually converge in some pretty fascinating ways.
Ooh, a physics rivalry.
You could say that?
I'm hooked. We'll have to pick up this thread in part 2.
Definitely. There's a lot more to uncover.
Sounds good.
Yeah. Welcome back to our deep dive into the life and work of Richard Feynman.
So last time we left off with these mysterious, strange particles, like shaking up the world of particle physics.
Right. They were like these unruly guests showing up at a perfectly organized party.
Yeah.
You know, defying all the established rules.
So how did Feynman handle this new puzzle? I bet he wasn't one to just back down from a challenge.
Absolutely not. But as always, he kind of took a different path than most. Instead of getting caught up in the theoretical debates about the nature of these particles, Feynman focused on what he could actually observe, what he could actually calculate.
That sounds like him always grounding his thinking in reality.
Exactly. And that led him to develop the Parton model.
Okay.
It was a way to explain the experimental results without getting bogged down in whether quarks, which are these theoretical building blocks of these particles,
Right.
whether they were real physical things or just a convenient mathematical tool.
So it's like saying, hey, we're getting these readings, and this model explains them, whether or not quarks actually exist.
That's a great analogy. It was a very pragmatic approach focused on what worked. The Parton model allowed Feynman to make sense of all this complex data coming from particle accelerators without getting lost in the philosophical weeds.
Meanwhile, Murray Gell-Mann was approaching the problem from a more abstract angle,
Right.
with his eightfold way,
Yeah, the eightfold way.
which focused on the symmetries between these particles.
Right.
Like two completely different languages trying to describe the same thing.
Yeah, and the fascinating thing is that both approaches were actually leading to a deeper understanding of the subatomic world.
Huh, okay.
Feynman's Parton model and Gell-Mann's eightfold way, despite their differences, both contributed to the development of the quark model.
So the quark model is the one that says that protons and neutrons, the
Yeah,
stuff inside atoms, are actually made up of these even tinier particles called quarks.
precisely. It was a revolution in our understanding of matter. You know, it's like discovering that the bricks making up your house are themselves made of even smaller, more fundamental building blocks.
Okay, my mind is officially blown.
Yeah.
But hold on. I remember the biography mentioned something about Feynman already looking beyond this.
Yeah.
Envisioning manipulating matter at the atomic level.
That's right. Even as the quark model was taking shape, Feynman was already leaping ahead. In his 1959 lecture, there's plenty of room at the bottom, he laid out the principles of what we now call nanotechnology, decades before it became a reality.
So he was talking about nanobots and manipulating individual atoms way back then.
He was. It was a truly visionary lecture. He imagined building tiny machines, storing information at unimaginable densities, even performing surgery on individual cells.
He actually talked about fitting the whole Encyclopedia Britannica on the head of a pin.
He did.
That seems like pure science fiction at the time.
It did, but Feynman's intuition was spot on. He saw the potential of working at the nanoscale.
Yeah.
And today, we see those ideas coming to fruition in fields like materials, science, electronics, and medicine.
It's amazing how he could connect his deep understanding of physics to these wild ideas about the future.
Yeah, he was really ahead of his time.
Yeah, but while Feynman was dreaming of tiny machines, his personal life was taking another turn.
Right. After a series of relationships, he met Gwyneth Howarth, who became his third wife.
Okay.
They built a life together, and Feynman, seemingly for the first time, really embraced family life.
It's interesting to see how even a mind like Feynman's craved connection and stability.
It shows that he was more than just a brilliant scientist, right? He was a man with desires and emotions, seeking fulfillment in different aspects of life.
And amidst all of this, he was also becoming known for his unique teaching style.
Yeah.
The biography mentions this course he created called Physics X, where students could basically ask him anything.
Physics X was legendary. It wasn't about memorizing formulas or regurgitating textbook knowledge.
Yeah.
It was about fostering genuine curiosity and a love for exploring the unknown.
I can only imagine the kinds of questions he got.
Oh, I'm sure they were all over the place. But even with his unconventional approach, there was no denying Feynman's impact on the world of physics.
Yeah.
In 1965, he received the Nobel Prize,
Wow.
shared with Schwinger and Tominaga for his work on QED.
It's amazing.
It was a well-deserved honor, recognizing his contributions to our understanding of the fundamental forces of nature.
But from what I've read, Feynman wasn't one for pomp and circumstance.
No, not at all. He actually considered turning down the Nobel Prize.
Really?
He did. The formality and attention made him uncomfortable.
Huh.
Feynman was always more interested in the ideas themselves than in accolades or recognition.
So he seemed to embody the spirit of pure intellectual curiosity, always pushing the boundaries of knowledge,
Yeah.
never satisfied with easy answers.
Absolutely, and that's what makes him such an aspiring figure.
Yeah.
He showed that science isn't just about equations and experiments, it's about a way of thinking,
Okay.
a way of looking at the world with wonder and skepticism.
And sometimes that way of thinking could lead to unexpected places.
Right.
Like when he was called upon to investigate the Challenger disaster in 1986.
Yeah, the Challenger disaster. That was a tragic event.
It was.
Feynman's role on the commission was pivotal.
In what way?
Well, he cut through the bureaucracy and technical jargon to get to the heart of the problem.
I see.
He famously demonstrated the cause of the disaster with a simple experiment.
Oh, right, with the O-ring. Right.
Exactly. Dipping a piece of the O-ring material into a glass of ice water, showing how it became brittle in the cold.
Right.
And that simple act, broadcast on national television, exposed a critical flaw in NASA's decision-making process.
Wow.
And it really emphasized the importance of clear thinking and scientific rigor.
So it's amazing how he could apply his unique approach to problem solving to something as complex and tragic as the Challenger disaster.
It showed that Feynman wasn't just a theoretical physicist. He was this brilliant mind capable of tackling real-world problems with clarity and insight.
So we've seen Feynman journey from the complexities of the quantum world to the potential of nanotechnology and even into the harsh realities of engineering failures.
Absolutely.
Right? It's an incredible story of intellectual brilliance, unwavering curiosity, and a deep commitment to truth.
It is.
But his story isn't over yet, is it?
Not at all. In our final part, we'll explore Feynman's later years and the enduring legacy he left behind.
Okay.
His impact on science and on how we think about the world continues to this day.
All right, on to part 3. Okay, so we're back for the final part of our deep dive into the life of Richard Feynman. It's amazing how much ground we've covered, from like the weird world of quantum mechanics to the tragic Challenger disaster.
Yeah, it really is. It's a testament to Feynman's just boundless curiosity and his impact on so many different areas
Yeah, for sure.
of science and thought.
So where did his intellectual journey take him in his later years?
Well, even as he was grappling with the mysteries of the universe, Feynman became increasingly fascinated by the potential of computers.
Okay.
He was particularly intrigued by this emerging field of quantum computing.
Oh, yeah, quantum computing. So that uses the principles of quantum mechanics to perform calculations that are impossible for like regular computers.
Exactly, yeah. So instead of bits, which are like tiny switches that are either on or off,
Right.
quantum computers use these things called qubits,
Okay.
which can be both on and off at the same time.
Right, because of that whole superposition thing.
Exactly, yeah. It's that mind-bending concept of superposition we talked about earlier.
Yeah.
Feynman saw the potential of quantum computing to revolutionize, well, everything.
Yeah, I can see that.
From drug discovery to material science to artificial intelligence.
It seems like he was always looking for that next intellectual frontier, that next big challenge to wrap his mind around.
Absolutely. And even as he was exploring these new areas, Feynman remained deeply committed to teaching and mentoring.
Yeah, he was a great teacher.
He had this incredible gift for explaining complex ideas in a way that was both clear and engaging,
Yeah.
making even the most abstract concepts accessible to anyone.
His Feynman lectures on physics, they're still considered classics.
They are. They are.
Inspiring generations of students.
Yeah.
Even captivating people who don't have a science background.
Those lectures, they really capture the essence of Feynman's teaching style.
Yeah.
It was this blend of rigor and humor
Yeah.
and a genuine passion for sharing the wonders of the universe.
It makes you feel like you're right there with him,
Yeah.
exploring the mysteries of nature.
Absolutely. And beyond the lectures, there's so many stories about Feynman's interactions with students and colleagues, always asking questions, challenging assumptions, just encouraging people to think differently.
Yeah, he seems like he had this incredible knack for cutting through all the noise and getting to the core of an idea,
He did.
whether it was a complex scientific theory or just a simple everyday phenomenon.
Yeah, absolutely. But even with all his intellectual brilliance, Feynman never seemed to lose that, that childlike sense of wonder,
Right.
that joy in simply playing with ideas.
Yeah, I read about all the pranks he pulled.
Oh, yeah, there are countless anecdotes about his pranks, his love of drumming, his fascination with safe cracking.
Yeah, it sounds like he was a real character.
He was, yeah. He was this vibrant, multifaceted individual who embraced life with gusto and never took himself too seriously.
And it's that combination of genius and humanity, I think, that makes him
Yeah.
such an enduring figure.
Absolutely. Sadly, Feynman's journey came to an end in 1988 at the age of 69 after a long battle with cancer.
Oh.
It was a huge loss for the world of science and beyond.
Yeah,
But his legacy continues to inspire and influence us to this day.
absolutely. His work on QED is still a cornerstone of modern physics, and those Feynman diagrams are now used by physicists in all areas of research.
Yeah, and his visionary ideas about nanotechnology,
Right.
they sparked a revolution in material science and engineering, leading to the development of just incredible new technologies that are shaping our world.
And perhaps most importantly, Feynman's way of thinking, his approach to science, continues to serve as a model for how we should engage with the world around us.
I agree. He taught us to be curious, to question everything, to never stop exploring,
Right.
and to always be open to new ideas and new perspectives.
It's like he was saying, don't just accept what you're told. Go out there, experiment, make mistakes, and most importantly, have fun along the way.
Yeah, that's the essence of Feynman.
Yeah?
He showed us that science isn't just about memorizing facts or solving equations.
Yeah.
It's about a way of being, a way of life, a journey of discovery that's driven by curiosity and wonder,
Okay.
and a deep love for the universe and all its mysteries.
Well, that wraps up our deep dive into the life and legacy of Richard Feynman.
It does.
It's been an incredible journey, and I feel like we've only scratched the surface.
There's always more to discover with Feynman. His writings, his lectures, his stories, they're all treasure troves of insights and inspiration.
So, what stands out to you from everything we've discussed? What about Feynman's life and work sparked your own curiosity?
I think for me, it's Feynman's unwavering belief in the power of asking why.
Yeah.
He never lost that childlike sense of wonder, that thirst for understanding,
Right.
and it's something we can all cultivate no matter what our field of interest.
That's a great point. Feynman's legacy is a reminder that we're all capable of exploration and discovery, so go out there, ask questions, embrace the unknown, and never stop being curious about the world around you.
Couldn't have said it better myself.